Как-то плохо слышно.
О, так лучше. Мгм. In Fröhlich mechanism, what is considered that two electrons exchange with phonons, which are vibrations of the crystal lattice, and due to this, they attract each other and form Cooper pairs. Phonons in this case are not coherent, so they're just single quantum excitations of the crystal. Now, what I am proposing is that there is another mechanism possible, which consists of phonons that have condensed into finite amplitude uh, fluctuation. And so you can imagine this as a local Bose condensate of phonons that act coherently. And they are forming glue that make fermions to attract and to form Cooper pairs. Now, why these phonons should attract each other and condense? This is self-consistent mechanism because the idea is that these phonons attract due to coupling of fermions into Cooper pairs. So this is bootstrapped mechanism, self-consistent mechanism that due to Cooper pairing, electronic part of the system lowers its energy and provides attraction between phonons that provide Cooper pairing glue for fermions. So, okay, this works. Now, another important point is why QBall. The idea behind QBall is the following. This is so-called non-topological soliton. Uh, First, as you can see, proposed by Rosen, and then that was mathematician, and Coleman, Sidney Coleman, the physicist. The idea is the following. There is so-called Derrick theorem that tells you that two-dimensional, above two dimensions, you cannot have soliton of finite size, stable soliton of finite size in the system, which is described just um, uh, by some finite rigidity and finite correlation lengths uh, between the shifts, say, of the atoms. So you cannot form some localized region or finite size region to form this fluctuation of deformation of the lattice, which without a special condition, namely, if your Euclidean action, which is written here, for the M field, this is of course simplified phonon deformation amplitude field, and okay, tau is Matsubara time, beta is 1 divided by kBt, so this is finite temperature Euclidean action for this deformation field. And the point is that if this action possesses such a property that when you shift the phase of the field M homogeneously in the whole space, nothing changes. So this is U1 invariant global phase rotation symmetry. So then it was proposed that if you consider this phase shift as Matsubara time dependent with some particular frequency, but okay, frequency could be all only boson Matsubara frequency because this is Euclidean action. So T is temperature, 2 pi, n should be integer. And if you consider this field having this Matsubara time-dependent phase shift, um, then it proves to be that Derrick's theorem could be violated, and finite size finite size solution that minimizes this Euclidean action and looks like finite size soliton exists. And so this soliton was called then cubal. So it means that there is no long range deformation in the crystal, or if it is not a deformation, people consider it also exchange between electrons with the spin waves, spin density waves. So we don't need long range antiferromagnetic order as we know is present in ceramics, cuprates before they adopt and may become superconductors. So here we have only short range order, and this could be either charge density wave or spin density wave with finite size. So it means that when coordinate r does not belong to the volume of the cubal, there is no deformation, it is zero. And this finite volume solution exists due to this trick with Matsubara time-dependent phase of the deformation field. Then one should introduce so-called d plus one dimensional current density, which has usual current density and time component of current according to this formula, which is more or less trivial. And then the U1 conservation, U1 invariant symmetry, U1 symmetry leads to conservation of so-called neutral charge of a cubal. So if you form such integral from the time component of this current, you will see that its first derivative is as function of time, first derivative over time is strictly zero.
What is A?
What?
A, the differentiation goes over A.
Alpha. Here?
Alpha?
Oh, this is alpha. So this is could be either three-dimensional x, y, z or time. So these are four coordinates. This is d plus one dimensional current density. So so we take now alpha equals time, and then it is time derivative, Matsubara time derivative. And when you substitute this expression into this formula, you will get this expression. That, what does it mean? Here is omega. This is this Matsubara omega standing here, rotation frequency in Matsubara time. M squared, this is square of the amplitude of the local deformation. This could be either spin wave or phonon field. V is finite volume of the cubal. So outside this volume, the M equals zero. And this is strict result. And what is important here that you see that this quantity Q capital is conserved, so it does not depend on Matsubara time. And in principle, it is proportional to the number of spin density waves or phonons condensed in this soliton. What is also important here that you see the product of omega, but omega is actually temperature, you see, because it's 2 pi times temperature if you say take n some integer, for example, 1. So the temperature times square of the amplitude of the fluctuation times its volume is constant. It means that if we increase volume, the m squared should decrease at constant temperature. So the entire inverse proportional because Q is conserved. And this was noticed by experimentalists who this
Volume should depend on parameters of the action.
yes, we will go further on. But if you found a cue ball and its charge Q is conserved, so you may have many different cue balls with the same Q, and then these cue balls would differ by relation between volume and amplitude squared. That's the idea. Yes. Thank you for this question. So this was noticed by experimentalists because they have measured um, so-called puddles of charge density waves, localized puddles of charge density waves in cuprates with macro X-ray diffraction. And this was done in mercury high TC compound, mercury barium copper oxide, and they found this funny results. So these are experimental points, and here, for example, these experimental points show that starting from some finite amplitude, the volume of the puddle decreases along this curve. A curve is theory, which I'm telling about. So curves are theoretical results and points are experimental results. So indeed, they found that the scattering amplitude, the increase of scattering amplitude causes decrease of the volume of the puddle. So and if you consider scattering of X-ray on the cue balls, then the amplitude is if you consider that the amplitude is this m, so then you see it's indeed so. And also what they found, they finally compiled the product of the experimental points for different temperatures, different amplitudes, and different volumes, make this product together and found these points. And here it is so-called T star temperature, below which so-called strange metal and high TC cuprates appears. So some pseudogap, linear temperature dependence of the resistivity, and so on. So, and they indeed found, and this is theoretical curve again, that follows from this very simple relation. Now, of course, let's go to the details. As you asked, as you said, of course, we should find out what is this amplitude m, on what it depends, and so on. So let us consider free energy, which is temperature times Euclidean action. What is important here, what I would be talking about, that's most important, it is UF. UF, this is energy of the cubal field M that appears after you integrate out fermions. So if you integrate out over fermionic condensate, this UF manifests that pairing glue that I was telling about. So it lowers the energy of the um, field M. And we shall find in analytic way this function later on. So now what we have, let us minimize, let us do the following. So you see this is first derivative over Matsubara time modulus squared. So it gives you omega squared m squared. And now if you use this relation, the Q charge conservation, this Noether charge conservation, you can substitute this omega squared with this expression, and you see volume appears in the denominator. Here, volume is in the numerator. And if this expression is positive, you have really minimum at finite V. And this is a cubal creation event. So you can find volume V, which is finite, that minimizes this Euclidean, effective Euclidean action of the M field. And then when you use this relation again, you can write this equation. So you see that Q charge cancels and you get self-consistency equation for the M field. So indeed, it depends on the parameters, on these coupling strengths between fermions and say phonons or spin waves, and on this correlation length, bare correlation length of these fluctuations of the lattice or spin fluctuations. And what is also important that if you substitute this solution back to here, you will find the energy of the cubal. And this energy of the cubal proves to be proportional linearly to the Matsubara frequency, which means it's linear with temperature, because Q is temperature independent, G is temperature independent coupling constant. And that's very important because then when we further on we'll consider the Boltzmann distribution of cubals over their energies, you will see that in the exponent, Boltzmann exponent, temperature cancels, because when you write down e to the power minus eq over kBt, t goes away, and you see it depends on q over g, and q over g, it is actually the number of condensed uh, excitations of spin or phonons condensed in this cubal. Um, so now, this was published in 2022. So it says that attraction between speed charge density waves or
Part where there is derivative over coordinate.
yes, we'll come to this. At this moment, it is considered here that you have just step function. So you have m, which is non-zero inside volume V, and it is zero outside this volume. So then this term is the gradient term here is absent, but we shall of course consider this later on in a more precise way. So this term was thrown out. Now, so this is bare.
Простите,
Да,
простите, можно вопрос
да,
к предыдущему слайду?
да.
Вот минимальная энергия, вы говорите, не зависит от температуры, но вот я, видимо, не
Она
понимаю,
зависит,
что...
она зависит от температуры, но она линейно от нее зависит.
А вот почему она линейная? Смотрите, Q ведь тоже пропорционально омега.
Дело в том, что Q это интеграл, Q не пропорционально, значит, сейчас, не пропорционально омеге. Вот что такое Q. Q это вот этот интеграл, это сохраняющийся заряд, который не зависит от тау.
Так.
А
Но, видите, он зависит от омега.
что?
Он же зависит от омега, значит, от температуры.
Да, но там стоит произведение омега, омега. Здесь стоит произведение омега м квадрат и v. Вот это произведение, оно все не зависит от температуры. А вот каждый множитель внутри, он, да, зависит.
Мгм. А выбирается именно n равно единице, наименьшее.
Да, это мы
Да?
сейчас, да, совершенно верно. Пока что, на самом деле, можно взять любое n, но мы увидим, что когда n равно единице, мы получим не нулевое решение, минимизирующее это действие, при самой высокой температуре, которая называется в данном случае T со звездочкой. Если мы выберем n, то будет новое T со звездочкой, но оно будет, скажем, если n равно двойке, оно будет меньше, чем старое T со звездочкой, там, в 2 раза.
Мгм. То есть главное, что я, видимо, пропустил, это то, что вот Q – это ваша заданная величина, и m квадрат v подстраивается
Да,
к температуре. Да?
да. Но мы еще увидим, как выглядит функция распределения Q а, с учетом того, что у куперовских пар есть корреляционный радиус Гинзбурга-Ландау, и, в общем, при приближении к ТЦ ну, мы увидим, что просто некоторые Q не могут возникнуть из-за того, что объем начинает расходиться, но это я расскажу чуть позже.
Хорошо, спасибо.
Вот, значит, хорошо, это был эксперимент, теперь мы переходим... yes, sorry. Yes, now in English. So these are self-consistency. This is self-consistency equation that we found by minimizing this effective action. And now it is most important to find this UF. So attraction between quanta of M field that causes actually a non-zero solution of this equation. So how to get it? We consider just usual Hamiltonian. You can obtain, for example, this Hamiltonian from Hubbard Hamiltonian by decoupling the fermion on-site repulsion by Hubbard-Stratonovich field M. Yeah, and then this actually corresponds to the action of this Hubbard-Stratonovich decoupling field. So the idea is the following, that if we take this fermionic action coupled to this M field, then if we would be able to integrate out fermions, we should get this effective action with this UF. And of course, because we are interested in effect or due to Cooper pairing, we consider this contribution of two Gorkov anomalous functions, this f dagger f, and what is this? This is correlation function of this M field. So it means when you take this interaction Hamiltonian to the second power, here you will get this loop. Извините, ради бога, мне нужен в туалет, буквально минутку. Здесь есть? Ага, сейчас.
Этот ток все это сохраняется, значит, ну, откуда он Q, вот, интеграл. Явление непрерывности как бы не было доказано.
Ну, это в любых теориях так. Ну, это теорема такая есть. То есть, значит, есть какая-то группа, которая вероятно устраняет действие.
Обычно
Будет ассоциированный ток. Если это группа определенная,
обычно должна быть
Группа
да,
один,
да,
ток
дивергенция
плюс один.
ну и вот и одно число сохраняет.
Это, нет, ну, чтобы оно сохранялось, нужно явление непрерывности.
Да.
Для этого тока размерности d плюс 1.
Ну, если там поставить поля, это как в уравнении Шрёдингера. Из уравнения Шрёдингера
Явление непрерывности.
да, все это то же самое. А поэт, видимо, ну, я не знаю, что,
Заряд.
да, не знаю, что они называются кушарами, но вообще, да, это такие, если заряд значит густыми постоянно, то он не выиграется.
Это интеграл от нулевой компоненты тока. Взаимодействие между электронами, приводящие к куперскому спариванию устроено фононами, а сейчас электроны сами приведут к некому взаимодействию между фононами.
Ну, то есть
Ну, У он сейчас будет выводить из фоне электрона. То есть эффективное взаимодействие между фононами.
Okay, so what is done then? We calculate contribution to this free energy of the system.
What is QDW in action as
Where is
C dagger Q plus Q zero?
Oh, here.
Yes.
Oh, this is creation and annihilation operators of the fermions.
I understand. But Q.
Oh, yes, thank you. Thank you very much for your question. This is very important because what is considered here that this charge or spin density wave has some preferential wave vector. So this is either single charge or single spin density wave. And we shall see where this preferential single wave vector comes from. It comes from nesting of the Fermi surface because it is known that in cuprates there are so-called anti-nodal points on the Fermi surface, and we consider that they are nested by this Q vector. So this is nesting vector. So in this theory, everything looks crazy, but I hope it's correct. Usually people would say if you have nesting, you will have charge density wave or spin density wave. No, guys, at high temperatures, you will have Kuba first. And then it is shown in the second publication, which is also in the list, that the TC of spin density wave transition or charge density wave transition is lower than what I'm telling you about T star, TC, superconducting, and so on. So thank you for this question. Yes, Q is important. And then when you integrate over space, this R is relevant here because we already integrated over space. And so because it is Q density wave dependent, you have this Q plus Q dV and simply Q. So this is usual. And here this integral should be. Well, okay, I see the point. What does it mean, this interval? This is where we integrating over the volume of the cubal. So this is free. This is fermionic action due to cubal. So this is integration over cubal volume, and here we have already integrated over the cubal volume over this R. So in principle, this integral should not be here anymore. So it's just Fourier summation, Fourier integral, which is left. So now what we see here is the following. We calculate this FF loop with d of omega. This is product m times m Fourier component with frequency omega, as we already discussed it. And of course, it would be not enough if we just calculate single loop. You may say, what is about high orders? So to calculate high orders and to take here full Gorkov Green's functions, you can use this trick, which is well known from HD. Oh, why it doesn't? Sorry, I don't see why. Yes, I'll show this somewhat later, how this is done. But in reality, what we do is the following. So suppose, no, it's not enough. I don't know why it jumped here. So let us now see what is the Gorkov-Green's function looks like. So for this, so this is the energy, the correction to the denominator of the Gorkov-Green's function, and this is actually a Rashberg equation. So what we see here, it is self-energy of the fermions in the anomalous Gorkov's function. This is D. This is correlation function of the M field. And this is actually Eliashberg equation. What is this difference with the usual Eliashberg equation? That we do not have here summation over Q, because Q is a single wave vector of the deformation in the Q ball. And all the rest is as usual. And it proves to be that this equation, if you write down the Gorkov's anomalous Green's function in this standard form, in Matsubara in Euclidean space, you can get that this Green's function with this Eliashberg-like equation exactly obeys the Mathieu equation of this shape. So this is exact result of this relation. So F, this is tau dependent Fourier transform in real space, but tau dependent anomalous Gorkov-Green's function. D, this is this expression because again we have Q-ball density wave which has only single Matsubara frequency omega, and G sub 0 squared, this is this is the following. This is actually the square of the superconducting gap, but yes, because what is G sub 0 squared? This is the sum of the bare electron dispersion function, electron energy, with respect to chemical potential, and this is self-energy sigma 2 modulus squared. The sigma 1 was also calculated, but it just renormalizes slightly the Fermi velocity and shifts the chemical potential, so we throw it away. And then if you assume that G sub 0 squared is related to sigma 2 in this way, you get exactly this Mathieu equation. It's Mathieu equation because this so-called potential is actually cosine omega tau. Now, what is important? We know that Gorkov-Green's function is changes sign when you shift by one period in Matsubara time. So it means that you should look for the first level above the lowest level eigenvalue of this equation, because we know that lowest eigenvalue corresponds to even function, and we need odd. So to get odd solution of this Schrödinger actually like equation, we should look for the first excited level state of the Mathieu equation. And sorry, I don't know what happens. Something is wrong here, but and then this is the solution. So you can, in reality, here should be not exactly one. There is some coefficient gamma, which is a order of 1/2. But if you take any handbook, textbook, you will get that the first excited eigenvalue of Mathieu equation is like this. Well, this is very important because you see that this solution appears only when amplitude m becomes greater than omega. So it's not, it means that the Cooper pairing would be first order phase transition with respect to amplitude m of the Q ball. So you cannot get a Q ball of arbitrarily small amplitude, because then you have no solution of the Mathieu equation of the first excited state. Well, this is well known that in the very shallow one-dimensional potential well, the lowest level always exists, but the first excited, the second level only comes when the depth of the well has finite value. And this is manifestation of this well known from elementary quantum mechanics fact. Now, after all, we can make a salvation to higher orders. Okay, first of all, here we got F to all orders in M because we have solved the Eliashberg equation. Well, of course, it's pseudo-Eliashberg because there is no summation over omegas. Second, why we are allowed to substitute this this complete f functions here? There is some special trick. I don't see why it is not here, but you know that if you introduce some coefficient alpha, which ranges from 0 to 1 into interaction Hamiltonian, you can differentiate this free energy over this parameter alpha and then calculate to all orders the first derivative over alpha and then integrate over alpha back and you get complete contribution. So this is what was done. And then, sorry for that. No. Oh, I'm sorry. This is wrong PDF file. That's the point. Somehow, is it possible to change? Because это точно не тот. Да. Я поэтому не узнаю, я смотрю. Я специально приготовил. Это, видимо, старый файл. Сейчас давайте посмотрим. Так.
Видите? Ну, вот это видно.
Так. А можно вниз посмотреть? Еще. У вас так. Ну хорошо, давайте так посмотрим вверх. Давайте посмотрим. Ладно, тогда вверх смотрим.
Есть еще ПТ.
Может, PowerPoint тогда лучше сделать. Да, потому что это какой-то странный файл.
Yes. Там других нет.
Мгм. Да. По идее, это должно быть то, что нужно. Потому что это мой доклад в Лейдене, который я делал 2 месяца назад. Так, вот должно быть все правильно. Почему там перемешал?
Ну, все.
Спасибо большое. Извините. I'm sorry for this. So, okay, so now it works, yes. So, what is important here? So finally, we found this contribution to the free energy, to the Euclidean action of the whole system. It means that we have integrated out fermions, and we got this effective energy of this M field that forms a cubal. And now it's interesting to see how this effective energy looks like. And it proves to be, it looks like this. So what happens is the following, that below some temperature, so above some temperature where there is no solution of the self-consistency equation, we have just this term mu sub 0 squared, and if we neglect derivative and we consider, or if you neglect derivative, you have homogeneous, this is actually oscillator, and you have quantum oscillator parabola where energy is parabolic as function of amplitude. Now, when Cooper pairing appears, this UF becomes negative, and it makes this extra minimum, which is not at 0 amplitude, but at finite amplitude. And this first happens at some temperature T star, which we will see how it looks like. And then when you go down in temperature, this minimum becomes deeper and deeper and deeper. And finally, you can imagine that at some temperature, it may touch. Yes, so you see here temperature lowers. T is 0.32 in some special units. So at some temperature, it touches zero, and then you have bulk superconducting transition. So now this is precisely the picture from Sidney Coleman article for Q-ball formation. And the only difference is that he considered real time in Minkowski space, and here is finite temperature. And of course, he did not consider the origin of this minimum, while here the origin is strictly the Cooper pairing. So now we go further on, and we can solve self-consistency equation close to this T star temperature. And here, actually, if you take n equals 1, this is highest T star temperature, and then you see that the superconducting gap squared behaves like this. So it at T star, the superconducting gap becomes 0. But as we have seen, the amplitude of the Q-ball deformation, spin or charge density deformation, starts from finite value, because we have seen that Matthew equation otherwise doesn't have second level appearing in the potential well. So in that sense, the Q-ball transition is first order with respect to Q-ball amplitude and second order with respect to superconducting condensate inside the Q-ball. That's very funny, actually. So now this limit, you remember that mu sub 0 squared, this is actually mass of the M field. So this is inverse correlation length of the charge fluctuation or spin fluctuation squared. G is a coupling constant between phonons or spin waves and fermions. Nu is the density of states at the nesting point, at the Fermi surface, at the Fermi level. And when this is much less than 1, we call this strong coupling. So now what is also important here, so please notice that when we go away from T star and in the region where this term becomes negligible with respect to 1, because G is here in the denominator, M becomes linear temperature dependent, which is important for us. So there would be region of linear temperature dependence of the amplitude of the Q-ball deformation, Q-ball fluctuation. And now this is the result of that procedure, HGD procedure, because we were called Zelenshinsky, with this alpha prefactor integration that gives you exact expression for this effective energy of the Q-ball deformation due to Cooper pairing inside the Q-ball. So this, if you take this integral, in principle, you get it. What is epsilon sub 0? Epsilon sub 0, this is a region in energy around the Fermi level in which nesting is valid. So outside this region, there is no nesting. So it's finite energy widths. Okay, so this is UF, and what you can do, you can now substitute this expression back into our self-consistency equation from which I have started, and solve actually it for this M. So this was your question, what is M, how it depends on parameters, and that's very interesting what happens then. Yes, and if we do this, okay, so now one more important story. What happens when we are close to T star temperature? When we are away, okay, M is proportional to omega, but when we are close to T star temperature. G sub 0 squared goes to 0. And it means, this is actually your question about temperature dependence of all parameters of the radius of the cubole of M and everything. We know from Ginzburg-Landau equation, just usual, so consider just usual Ginzburg-Landau inside the cubole for superconducting Cooper pairs condensate. In close to this zero here, zero of the gap, we can linearize Ginzburg-Landau equation in this way, and rho is the distance from the center of the cubole to its volume, inside its volume. And then you have this Ginzburg-Landau equation with B, this is just some parameter of Ginzburg-Landau which stands in Ginzburg-Landau functional. So it means that the radius should be such that the left part should not be bigger than the right part. And if G sub 0 becomes very small, the radius at which this left part becomes greater than the right part tells you what is the minimal size of the cubole. So this is well-known problem from, say, Landau-Lifshitz volume 9 part. This is statistical physics part 2. What should be the size of the superconducting sphere, at which superconductivity disappears, and so we get this expression. So 1 over Rm squared should be less or equal b G sub 0 squared. And when G sub 0 squared goes to 0, at T star, R goes to infinity. So it means that we have minimal size of cubole, and it diverges as this power, T star minus T to the power 1/5. And then we shall use this when we do the Boltzmann distribution function, because as you remember, the Boltzmann distribution function in the exponent has exactly this value of cubole charge Q. So it means that when this value diverges, the probability to find cubole goes to 0 at T star. So now, okay, this is what I already told. So this is a behavior of Q mean, and this is how actually this expression close to T star follows the experimental points, because indeed, when Q minimum goes to infinity, you will see that these experimental points really diverge. And well, what is here is, of course, questionable, but this is above T star. So this is theoretical curve, and this is same theoretical curve with the experimental points. So it means that these experimental points actually show that indeed the superconducting condensate of Cooper pairs appears inside the cubole, and when we come close to the temperature when it appears, the Q minimal value of the cubole diverges, and that's why these points diverge. It would never be in usual superconducting theory, because in usual superconducting theory, you can get as small vanishing phonon amplitude as you wish. Here, the role of coherent phonons is played by this amplitude m, and we know that it starts from finite value m equals omega at T star. So that's manifestation of these cuboles. Now, and finally, I promised you to show what are self-consistent solutions for the amplitude m. So now, if we fix omega, um, and we are below T star, and now we are coming to the question why Tc is high and what is T star and what is Tc. The next few slides. So this is our self-consistency equation. If we substitute here this effective energy of M field due to integrating out fermionic Cooper pairs, we get these solutions. So what this is very interesting because you see what happens. So what are these contour plots? Contour plots, these are points in the axis of temperature and amplitude m divided by omega, where this equation is obeyed. So when this is zero. So these are 0-point contours. Now, what is G nu? If you remember, nu is density of states as a nesting region at the Fermi surface, as a bare Fermi surface, and G it is electron phonon or electron spin wave coupling constant. So what this plots show you that when we increase G nu gradually, the solutions of this equation form this curve, this different family of curves, and they become deeper and deeper in temperature. And what is also important, that for each G nu, actually you have two regions of solutions. One region of solution is close to T star, and another region of solution is close to zero. So you see, it looks very much like the phase diagram of high TCs because you have superconducting dome, which is obtained due to this lowest branch for each fixed G nu. And you have strange metal region, which is obtained for upper branch of solution for each fixed G nu. And when G nu grows, finally you get special G nu value when upper branch touches the lower branch. And then you see this is indeed optimal doping because then you have this T star becomes equal to Tc. And now, of course, it is interesting to find out how this parameter mu sub 0 and G and nu define these temperatures T star and Tc. Well, of course, when we are above, then you see that you have T star 0 and T star 1 of this strange metal region. And okay, you go from here. For example, if you start on this branch, here the first solution appears and here it disappears. So you have strange metal region in temperatures T1, T2. But oh, I should go further fast. So it is possible to find out the dependence of T star and Tc as function of the coupling strength, which is G nu epsilon 0. This is G nu epsilon 0 divided by omega. No, not by omega. This is omega star. But anyway, so, and then we can find out the absolute values of temperatures on this branch, which we call strange metal region, and this branch, which is superconducting bulk superconducting phase. You see, this is the answer. So when Tc touches T star, the value is just mu sub 0 over 2 pi square root of 3, and the maximum T star at which first cubal appears is this one. So this mu sub 0 is known from John Tronquada experiments on spin waves in doped high Tc cuprates, and it gives you inverse correlation lengths because he measures the width of the resonant peak for spin waves, and it's indeed around 100, 200 kelvins, and that's why TC is high, because you see that the highest optimal TC is of order is mu sub 0 over 2 pi. So it's just defined by the inverse correlation length of the fluctuations either of charge or spin that are involved in Cooper pairing. Now, it's not much time left. Okay, now this plot here on the left, this is, as we have seen, these are temperatures at which there are solutions of self-consistency equations. But you may ask, okay, this is the phase diagram, and when you go with doping, it looks like that. Why here we have only half of it? The reason is very simple, could be very simple, because here what we have on the horizontal axis is this coupling strength at the nesting region of the Fermi surface. Now, if you consider, for example, extended Van Hove similarity, then this coupling strength as function of doping is not it has a maximum. So it means that when you deconvolute this plot, substituting instead of coupling strength at the nesting point with the doping dependence, you get indeed this deconvolution of this plot into two parts. And so you get this picture of the phase diagram, which looks more or less like the strange metal diagram. So the major point here is that everything that I was telling about is produced by what is called thermodynamic time crystal. This probably was invented by Konstantin Yefetov, who worked also at our department as a grant leader for some time. And what does it mean? That you have densities which have zero average value, but finite amplitudes. And these densities, spin or charge, may cause Cooper pairing, as I had demonstrated, or tried to demonstrate. Next, what we come, so I should probably shortly, but in principle, you could consider electrons which are not in cuboles, which are outside cuboles, so they're in normal state. And there are Cooper pairs which are inside the cubole. So electrons may be scattered by this deformation of the cubole amplitude field. This spin or charge density wave local fluctuation, which is cubole, so they would be scattered by it. And if you calculate such kind of diagram, you can find out what is lifetime of normal fermion, not paired fermions, scattered by cuboles, which are considered then as impurities, but with temperature-dependent amplitudes. And if you do this diagram and you can sum it to all orders just self-consistently, you get indeed that the inverse lifetime of not paired electrons really is linear in temperature in the regions where amplitude m is linear in temperature. And what even more important, that as we have seen, m just nearly equals omega without coefficients. So you see that this 1 over t just equals omega without coefficients. More detailed calculation, which is now on Konmath here, indeed gives this answer. So just Matsubara omega appears just with some numerical coefficients. And so these are details of calculations, but as I have no time to tell now what other manifestations of cuboles. You can also calculate because if you have cubole with a superconducting condensate inside, it means if you switch on magnetic field, this cubole would have currents which produce diamagnetic moment. And you can calculate what would be the diamagnetic moment of the cubole gas as function of temperature. And then you see these curves. they're calculated exactly. This is the answer to your question. How about coordinate dependence? Yes, indeed. If you not substitute the cubal by a step-like function, but you minimize the effective free energy of the Euclidean action, taking into account coordinate dependence, then you get this solution. So it goes exponentially to zero outside cubal, and it's nearly constant inside the cubal. And
What determines lambda?
uh,
Lambda is what? So this is
yes, lambda. Okay, roughly speaking, lambda is of the order of inverse correlation length of the fluctuation. This is very crude. In reality, it's not strictly so, but details are uh, here. And this is experiment by Lee and others who found this diamagnetism as function of in Bisco compounds, super doped compounds as function of temperature. And also so-called famous Uemura plot, if you know anomalous Gorkov's-Green's functions, you can calculate, of course, the density of superconducting density inside the cubal. And when you do all the calculations, finally, you get this, that the density of superconducting density inside the cubal is proportional to Tc, which is famous Uemura plot. The difference is, of course, that here this NS saturates in this way, but in Uemura it saturates in this way. That's what I don't know yet. So this is experiment, this is theory. But notice, please, that axes here are rotated. So the theory gives you only these linear paths, but cannot get this thing right so far. And also, you can calculate, as we discussed now, using this Boltzmann exponent and the density of cubals in the volume of the sample, which is just volume divided by the volume of the cubal, and this is probability of the cubal. You can calculate specific heat of the cubal gas, and just you get this plot, which has maximum close to T star, which also resembles experiment. And finally, when you know anomalous Gorkov-Green's functions, you can calculate actually the Ginzburg-Landau order parameter function psi, which is wave function of the sorry, you can calculate the wave function of the Cooper pair in the center of mass system of coordinates, and you find this so-called four-legged starfish shaped Cooper pairs, because you see that in the nodal direction in the Fermi surface, the nodal direction, the Cooper pair size is big, while in the anti-nodal it is small. And okay, this all was also calculated and published here. Finally, there are other cubal solutions which I have not shown, which are when you have not only omega frequency, which gives you time dependence of the m of tau as function of Matsubara time, but you can have more, besides the omega frequency, also oscillations of the amplitude itself, and these solutions are also possible to find. And then you get extra cubal solutions with the condensates. Inside this this here, which probably would correspond to these regions where experimentalists also find something strange, where experimentalists also find pseudogap, but no superconductivity, no bulk superconductivity. And okay, so what are perspectives? Of course, it is interesting to find out what are the excitation spectrum of the cubal, because what I have found is just the saddle point solution for the Euclidean action, effective Euclidean action of the charge density wave or spin density wave. But there are also phonons or spin waves inside cubals, and spectrum could be measured experimentally, and this is what is going on now to the calculation of this, to predict it, what this theory gives. And also what I also wanted to notice, it is not shown here, but it proved to be the following, that if you do this loop, if you do this loop that gives you contribution effective to effective energy UF, you can do it from this interaction Hamiltonian for the spin wave and for the charge density wave. What is interesting, I'm looking for, oh yes, here, the interaction Hamiltonian. So if M is spin density wave, so is the density of local spin interacting with the fermions. So then you have spin projection sigma. And then this loop, in order to make it negative, the order parameter should be D wave. Because here, one electron has spin up, one electron has spin down. So if it is spin singlet superconductivity, in order to make this loop negative, the vector Q, this Q density wave vector, should connect regions of the Fermi surface, of the bare Fermi surface, with the opposite signs of the superconduction order parameter. And this is indeed found in the high TC cuprates. But what is also interesting is that if this M is a charge density wave amplitude, then this sigma is not here. We know that when you decouple Hubbard Hamiltonian with Stratonovich fields, there is term also without sigma. Then, in order to this loop to be negative, you should have S wave. And indeed, experimentalists now say that they have seen both S wave and D wave kinds of superconducting behavior in high TC cuprates. So it's funny, but this simple derivation also explains why it may be so. Well, sorry for this strange story, but
Let's end.
thank you for your patience.
Let's start from questions in Zoom. Please. But you should ask in English, Vladimir.
Okay.
Please.
May I ask?
Yes.
Yes, yes.
Is it possible to understand in fingers why the resistivity is proportional, is linear in T? So you see, if I consider scattering of electron by Q-ball just perturbatively, like Fermi-Golden rule, then I would expect that the scattering rate is proportional to the square of the amplitude of M. And amplitude M is proportional to temperature. So I would expect, naively, I would expect that the scattering rate is proportional to
Temperature squared.
To temperature squared.
Yes, thank you very much for this question. this is a slide where I would like to do this. So if you consider here the size of the cubole, so when electron goes through the cubole, the uncertainty of momentum is HgBa divided by the size of the cubole. And the uncertainty of the energy of this electron due to this uncertainty of momentum would be V Fermi times delta P is this. So it's inverse proportional to the radius of the cubole. Now, if we consider the lifetime of electron in this state when it goes through cubole, then we have Heisenberg inequality that lifetime times discrepancy of energy, uncertainty of energy is greater than h bar, and then we get this relation that 1 over tau q that is proportional to Fermi times 1 divided by radius of the cubole. And now then when we look at this relation for the Q charge, which is temperature independent, when we divide indeed by omega m squared, indeed m proportional to temperature, then omega m squared is proportional to cube of the temperature. It means that volume is inverse proportional to the cube of the temperature. It means that radius is inverse proportional to temperature. And that's how you get this 1 over tau q proportional to 1 over RQ. But okay, this is on fingers. In reality, it is possible. It was calculated, as I said, just solving this integral equation and Dyson-like equation, and then you get exact result like this. So
May I ask the second question?
yes, please.
What is the interaction between different cuboles, between two cuboles?
Yes, thank you very much. This is very good question. This is actually what we are going to investigate now, because indeed the cuboles, first of all, they may exchange via the Andreev's reflection with the electrons which are outside and not paired. When two cuboles come together, there could be like a Josephson effect between those two cuboles with the tunneling of Cooper pairs. And I haven't told here lots of things, but in principle, I have no answer at the moment, but it is very interesting problem that we are trying to consider now.
But can you even do you know at least the sign of this interaction? Is it attractive or repulsive, or it is still open question?
What I can say, let me not to try to guess. I don't know.
Okay, thank you very much.
Thank you.
As far as understood, cubole contains condensate of phonons and condensate of Cooper pairs.
Yes.
And these two condensates interact with each other.
Yes.
Because one creates
exactly. One creates the other.
If we shift them, displace with
Yeah.
respect to each other, there's some oscillations made.
Yes, that's interesting. So that would be, that's actually one more excitation type in cubole, which of the M field itself. But
this would be like dominant excitation of the.
Yes, that's a very nice idea.
Plasmon.
Yeah,
like plasmon. Yes, there should be plasmon-like modes. Thank you. But this would be interesting plasmon, because this is excitation involving superconducting condensate.
Yes.
It's not usual normal density.
But the distinguishing feature of such an excitation is that the dipole. Like
yes, in dipole.
Relative motion.
Like,
So this dipole.
Like dipole.
This is the simplest You
No,
can
I mean-
imagine breathing mode.
Condensate has charge. Okay. it's
Yeah,
like net charge.
there
Net
could
charge,
be
yes.
breathing mode, like monopole.
Yeah,
One,
dipole.
It should be dipole.
Dipole mode. Yes, thank you for this interesting question. Yes.
I have also question, and I always thought that high temperature superconductors, they have specificity that they are layered,
Yes.
which means that there is some I don't know, some direction which is not equal to two other directions. But here you didn't take into account any of
Not
this.
yet, no. But in principle, yes, you can consider. The point is the following. So when we, in this strange phase diagram, the point is that when we are close to T star and when we are close to T star minimum, in both cases, the size of the cubal diverges. So it means that here in between, there should be some percolation phenomenon. And then if you have something layered, then it was just recent paper by one of our coworkers at the department, Pavel Grigoriev, who considered that when you have percolation cluster, it may appear first in the C direction and then faster than in the AB direction. So in principle, this may also be the case with the cubal gas when they start to percolate, but I don't know.
But QDW, this vector, this
Yes, here the-
vector,
Yes, it is.
what direction it
Yes, let me find in this strange PowerPoint file. There should be a plot. Yes, here the plot. So this is what people see as a because here would be whole pockets in lightly doped, then they see this kind of Fermi surface in 2D in AB plane. Then these are so-called anti-nodal points, which we consider as nested, but in this strange way nested with a cubal field. So this is cubal density wave, spin density wave. Now, there are other nesting vectors which are between this and this prove to be charge density waves. So that's
Okay.
the shape. And anti-nodal points, indeed, they are covered with a gap far above TC, and that's why this is so-called pseudogap. And okay, this is nodal direction. So this is D wave order parameter, as we discussed already. So you see, this vector really connects plus region of D wave with minus region of D wave, as we said, which is necessary to lower the energy of the cubal. And the charge density wave vector, if it forms cubal, would be between these 2 points. So it would be S wave.
Okay, if we don't have
I forgot, sorry, just to say that. And then in experimentally, these regions are so-called pseudogap regions, where there are when the fermion spectrum is really gapped, and which corresponds to condensate inside the cubal. So.
it's hard to imagine these phases on this plot, I would say. But if we don't have more questions, let's end.
Thank you. Спасибо большое. Спасибо.
Так, можно запись остановить?
Да.
Кстати,
Давайте выпустим.
возникновение этих шаров, оно меняет род фазового перехода?
Да.
Какой род здесь
Значит,
получается? Первый?